Consider a system of 4-point charges Q each placed on a straight line with adjacent charges A apart. This is A and this A and this A. What is the energy of this system? Let's get this calculation going by say counting the pairs. Well, we have to count the pairs without duplication. So we have pairs 1, 2, 2, 3, 3, 4 all identical. So each of them has energy of q squared by 4 pi epsilon 0 A. So U would be 3q squared by 4 pi epsilon 0 A. This is for the pairs 1, 2, 2, 3, 3, 4. Then 1, 3 and 2, 4. There are two identical pairs there. Plus, so two of them q squared by 4 pi epsilon 0 2A. Right? Then the pair 1, 4. That's just one of that q squared by 4 pi epsilon 0 3A. So that's the energy of the system by counting the pairs. The simplest way of doing it, I guess. So you get q squared by 4 pi epsilon 0 A common, and this is 3 and this is 2 and then this 2 here, so this is 1. So plus this is 3, 1 by 3. Right, 4 pi epsilon has gone out common, this is 3 and this 2 has gone away. So this is it. We can simplify that, right? That's 9 plus 1, 10, 11 by 3 into q squared by 4 pi epsilon 0 A. 11 q squared by 12 pi epsilon 0 A. That's the energy. We can also find the energy by imagining we configure the system. That is, we have only q and the other three are very far away. We bring each one of them and then place it at the final location that they are in. So when you bring q from very far away to this position, the work done would be, let's call it the total work done. That's q has been brought from infinity to a place where the potential is q by 4 pi epsilon 0 A. Plus this q is brought to the field of this q and this q. There are two of them. So the charge 3 has been brought to the field where the final potential is q by 4 pi epsilon 0 A due to this one and 2A, sorry, q by 4 0 2A, this is 2A plus q by 4 0 A due to this one. So q by 4 pi epsilon 0 2A plus q by 4 pi epsilon 0 A. This is the potential. So then the last q has been brought to the field of the other three. The potential here due to this q is q by 4 pi epsilon 0 3A, and due to this q it is q by 4 pi 0 2A, and this q by 4 pi epsilon 0 A. This is the work done in configuring the system. Lot of calculation here. We have not exploited the symmetry. There were 1, 2, 3 identical pairs, then 2 identical pairs of a different kind, and then 1 pair, 1, 4. So that was easy. 6 pairs. So this is the calculation you will have to do if you want to go for work done configuring the system. So choose whichever way you want to do. I would go with pairs if you have got a system of point charges. I'll find the energy of the system by counting the pairs without duplication. That would be the easier way. Yet another way of doing the calculation would be to go for sigma qi vi by 2. Do this calculation for each charge. So let's go to this charge and find the potential where it is due to other charges. Q by 0 A plus, let's call that q by 4 pi epsilon 0 to neighboring charges v. So this is v, and due to this it will be V by 2 because it's double distance, and due to this it will be V by 3, where V is the potential. V is basically replacement for Q by 4 pi epsilon 0 A. So this V is Q by 4 pi epsilon 0 A. We're trying to save ourselves some ink. Then go to 2. So this is the energy of the system U. Go to 2, and then that energy of Q will be, potential due to this will be V, due to this V, and this double distance of V by 2. So V plus V plus V by 2, V plus V plus V by 2, right? Then this third charge will be same as this. So this is 2 times. Then the fourth charge will be same as this first one, so twice this. So this will be, we can see 2Q comes out, V comes out, 1 plus half plus 1 by 3 plus 1 plus 1 plus 1 by 2. Well, you can work this out, and this V is Q by 4 pi epsilon 0 A. That will take care of the calculation. This is sigma Qi Vi by 2. Sorry, you must halve this. Sigma Qi Vi by 2. Half of this. So let's finish this off. This 2 gets cancelled. QV, and this is a 6 is LCM. Or this is 3, right? 3. 6 is the LCM. 3 into 6, 18. And this is 2 here. Or let's simplify this. Well, this is 2.5 here. So this is QV. 1 plus 1 plus 1, 3. 3 plus half plus half, that's 4. 4 plus 1 by 3. That is 4 plus 1 by 3. So that's it. And then perhaps you made a mistake in the previous calculation. Check that out. This be a calculation. The idea is go for sigma Qi Vi by 2. So right, this is I think everything is fine. So work this out, and then, well, that's the potential. This V is Q by 4.0. You substitute and you get the energy of the system. Let's calculate the energy of a distributed charge in a conductor. Now this could be a conductor of any shape. Let's say it's got a charge Q, and you want to find its energy. One way is to find the work required to be done to configure this charge. So you can imagine each of the DQ elements is very far away. It's being added to this element by element, and as it's being added, the potential raises here. When you do some integration, if the charge is Q at a moment and you're bringing dq from infinitely far away position, work done in that is dq into this potential would be some k times q, whatever charge that we have, some k times q. Q is a variable now. dq is being added at the moment when the charge, and this is q, and this being brought from infinity. So this is the work done. Integrate this as q change from 0 to qf. Now that would be K comes out, Q squared by 2 and QF, that's QF. Now KQF is the final potential, right, of this conductor. We said potential is linearly dependent on the charge. So this is KQF is V into QF by 2. Let's drop that subscript, and then this is the work done in building up the charge on this, so it will be QV by 2. This is one way, adding the charge element by element. Even this could be done a little differently by realizing that potential of this increases linearly. The first DQ element was brought when the potential was 0, and the final potential when it is got to the final DQ element when the potential is built up to the final value of potential, which is say V. Since V changes linearly with charge, the average potential difference against which the DQs have been transferred is V by 2. So that is a good idea. So Q has been transferred from infinity to this place, and the average potential difference, well, was of V by 2 minus 0 there. So this is the energy. Don't need to do the integration because it's a linear increase in potential as charge is being added. It's much like a situation like this. We have, say, material lying on the floor. You want to build a pillar. Now this is a pillar of uniform cross section. The final height of this is h. The material has been lifted through varying heights. Now first element nearly 0, then last element through h. So each dm element has been added at different moments, and the height has changed from 0 to final value of h. Since the height increases linearly with the addition of material, the potential, the height, average height against which this mass has been lifted is h by 2. So if m is the mass of this, mg h by 2 is the work done in adding this element, when this mass is element by element. So average height against which m has been added. Mind you, m and h are linearly dependent. So that's how it nicely works out. Of course, you can look at the final state and say the potential energy is mg h by 2 for this, 0 here. So change in potential energy, mg h by 2. We don't need integrations like, say, if the height is y at some moment and the increased thickness by dy, that mass of that dy element, say some k dy, right? And that's been lifted through a height y, right? So work done is g into y, mgh. K dy is the mass added, it's been lifted through height y. So integrate this from 0 to h, and that will give us the energy. This if you look at the process of building it up. But if you realize that it's a linear change of height with mass, then you can average it out and then say mass elements have been lifted through an average height of h by 2. So this is k into h will be the mass, right? K is dy is thickness, we said mass is k dy. So k into h will be, this will come out to what? kg integral of y dy, y squared by 2, that's the limit, h squared by 2, and kh would be m. So this is mgh by 2, but you don't need to integrate. But this is just to show that there's a linear dependence of height with mass, so you could average the height through which the mass has been lifted. Same thing here. There's a linear dependence charge being added to the conductor, so average potential against which charge has been transferred is V by 2. Let's calculate the energy of a system of point charges, 4 of them located on a straight line with adjacent charges A apart or adjacent charges D apart. Let's say there are 4 of them, all equal, and adjacent charges are D apart. Let's try out all options for the calculation. One of them is sigma Qi Vi by 2. Now, we need to find potential at the place where, say, the first charge is due to the other 3, and do the calculation for all others, and then halve the calculation, sigma Qi Vi by 2. To make it a little easier on us, let's say we'll use potential due to the neighboring charge as a reference. Like say the potential due to the second Q at the place where the first Q is Q by 4 pi epsilon 0 A. Let's call that VA, the potential due to adjacent charge. So we can refer to the potential due to other charges in terms of this. This charge is double the distance, same charge, double the distance. So potential will be, this will be doubled, so this will be, well, halved. Then 3 times the distance, this will be 1/3. So potential at the place where the first charge is due to the other two, well, we got to have sigma Qi by Vi by 2, right? So Q, first charge, into well, let's go to, so potential at the place where the first charge is, that's Q, into potential due to adjacent charge is VA, the other one which is at twice greater distance VA by 2, then the farthest one is VA by 3, right? We'll have a half here, we'll come to that later, let's put that half here, half. And what do you see here? The calculation for the fourth charge will be same as for the first one, so let's double this. And let's go to the second charge. The potential at the place where it is due to neighbor on the left is VA, neighbor on the other side is VA itself, and the other one which is at twice greater distance, that will be VA by 2. That's the end of the calculation, and again there a calculation for 3 would be same as calculation for 2, so twice this. And this will give us what? This half and 2 take care of each other, so Q and VA comes out common, and then we'll have 1 plus half plus 1 by 3 plus 1 plus 1 plus half. That's the calculation, right? That's QVA, and you can do this calculation: 1 plus 1 plus 3 plus half plus half, 4 plus 1, 1 by 3, 4 plus 1 by 3. So we have 4 plus 1 by 3, 13 by 3, right? 13 by 3, and this is VA. VA is this. So Q into VA, that will be Q squared by 4 pi epsilon 0 A. This sigma Qi Vi by 2. To go to each charge and ask what is the potential at the place where it is presented to others. Do this calculation for all the charges and then halve the calculation. The other calculation is to count the pairs and not duplicate. So it's like well, for example, 1 and 2 is a pair, and the energy of that pair, let's say energy that's in pairs, let's call that UA. That will be Q squared by 4 pi epsilon 0 A. Again, we can use this as a reference value just to make it a little simpler for us to write down. And other pairs, for example, can be energy of other pairs can be defined in terms of this. Because numerator is same, Q, product of any adjacent pair charges is Q squared. So what have we got here? 1, 2, 3 pairs, that is 1, 2, 2, 3, 3, 4, all identical, and this is the energy of each pair. So 3 UA plus, let's go to the pairs 1 and 3, that's double the distance. So if you pair 1 and 3, then 2 and 4 are similar pairs. So twice, this is 1 3 pair and 2 4 pair, and energy of each pair will be UA by 2, right? Then there is this 1 4 pair, that is the sixth pair, 3 of a kind, 1 2 2 3 3 4, then 2 of a kind, 1 3 and 2 4, and the last one, and this is thrice the distance compared to the adjacent charges, so that's UA by 3, so there is only one of that kind. So this is the energy of the system. This is a much easier calculation, right? So no halving here because we have not duplicated the pairs, right? And so that's 1 2 and not 2 1, 1 2 2 3 3 4, 3 pairs there. Then this is UA, that's q squared. This is 3 plus 1 plus 1 by 3, 4 plus 1 by 3, 13 by 3 UA q squared by 4 pi epsilon 0 A. Much simpler. So you can try this out. When there is symmetry, identical pairs, energy of one pair can be defined in terms of the other. This is very convenient, counting the pairs without duplicating, without repeating. One other method is to treat each charge as being in the field of the others and then leave out that from further calculations. This can be a bit tedious. Again, let's use q by 4 pi epsilon 0 A, that is the potential due to the adjacent charge at the place where one charge is. This is the potential due to the adjacent charge. Let's use that as a reference. Let's go to the first charge. This U would be first charge. What is the potential where it is present? VA due to the adjacent charge, and the charge 3, that is twice the greater distance, so VA by 2. Then fourth one, that's that 3 times the distance, so VA by 3. We'll leave this from further calculations. We'll leave this out. Then go to the second charge, potential at the place where it is due to 3. We'll leave out 1 from further calculations. We realize that charge must be treated either as being in the field or creating the field to get the calculation without halving. So this is Q, potential at the place where 3 is, that's VA due to 4, VA by 2. Then the last one, Q in the field of, we'll leave out 2 from further calculation. So now we are with 3 and it's in the field of 4, that's potential is VA. That's it. And this is Q comes out, VA comes out, 1 plus half plus 1 by 3 plus 1 plus half plus 1, and you can see this is half plus half, 1 plus 1 plus 1, 4, 4 plus 1, that's 11, 13 by 3, 13 by 3 Q into VA is that, so that's Q squared by 4 pi epsilon 0 A. This is another option. I mean, this doesn't exactly take care of symmetry in the system. And this would be okay if different, you had Q1, Q2, Q3, Q4, distance were not equal. Well, there's no duplicate, you're not calculating something and then halving like earlier. Here it is 1 in the field of 2, 3, 4, leave out 1 from the calculation. So you're left, the simpler system starts getting simpler and simpler. So you can try this option.